movie, we'll create a structural performance simulation model of an electronic box assembly mounted on the fan case of a gas turbine engine. We'll begin by creating a finite element model of one of the components, one of the brackets that supports the electronic box. The entire demonstration is being run in a managed environment under Teamcenter. Also for this demonstration, we have two users that will be playing parts. We have Andy, who is the analyst who is creating the structural performance model of the bracket, and we also have Ed, who's the engineer, who we'll meet a little bit later. So right now, Andy has created an idealized part of the bracket, which is an associative copy of it, which Andy can edit and modify to prepare for simulation. First, we'll create a mid-surface representation of the sheet metal bracket. And here you can see that the gusset has been extended into the adjacent faces. And we'll use this mid-surface model to create our mesh. To ensure that we have a congruent mesh, we'll first stitch the two sheet bodies together. And there's one thing I'd like to highlight here. There is some imperfections in the model. I'll undo that last stitch. So here you can see that where we have this weld, there is a gap in the model and things don't line up quite right. But using the search and snap distance tolerances, we can easily clean up any irregularities in the geometry. So next we'll create our 2D mesh. And since we're in the Nastran solver environment, you can see we've got a CQuad 4 selected at the top. And we'll also select certain mesh quality options to ensure that we have a good mesh. Now, as a double check, we can also see if we have any free element edges where we shouldn't. So I'll go ahead and turn off the geometry so you can see in magenta where all of our free element edges are. There's none here at the weld. There's also none where the gusset welds into the bracket. So here you can see we have a congruent mesh, so that's great. Next, we'll assign some physical properties to the mesh. Now Ed, the engineer, had told me earlier that he has already assigned a material property for the bracket. So all I need to do is inherit that material into my structural analysis model. That avoids potential errors in my material specification. Now for the thickness, and before we get to the thickness here, if you want to see what material Ed has assigned, you can see the objects that material 718 has been assigned to. So also for the thickness, we'll specify the thickness as being inherited from the mid-surface definition that we created earlier. And here we can edit the display of our structural mesh to show the thickness and any offsets that have been specified and compare that to our solid representation to confirm the thicknesses are correct. Alright, so that completes the specification of our support bracket. That support bracket is used in 4 locations, but we only need to create one model of it. Next, we'll create our structural representation of the electronic box, which is called a FADEC. So here I'll create my finite element model and idealized model part for the FADEC. And we'll begin in the idealized part. Same as we did in creating our bracket model, we need to create a mid-surface representation of it. So here we'll use the predictive toolbar in order to select the commands that we would like to perform. Here we'll go to delete face. We can select boss or pocket faces, or we can just select single faces as well and drag a rectangle around those features that we don't want to include in our simulation model. And if we get too many faces, it's easy to deselect with the Shift mouse button 1. Alright, so that predictive toolbar is handy. Otherwise we can go back to the ribbon to select the same commands. Alright, next we'll create our mid-surface. And for our finite element model, we don't need all of the bodies to be selected. It's a little bit sloppy earlier. I probably should have selected none as I did with the bracket specification. And then after we've created the mid-surface, we can just select the mid-surface and any specific solid bodies that we'd like to include. So here, all I had visible was the mid-surface plus the board components, which we also want. So we'll start off with creating a finite element representation of the board components. I'll go unshaded so that you can see what's happening a little bit more clearly here. We'll create a 0D mesh lumped mass at the center of gravity of those bodies, and it will use the mass properties defined from the CAD model in terms of the density. And here you can see it automatically puts at the CG of each one of those bodies a concentrated mass. Not only does it do that, but it also assigns a mass as well as mass moments and products of inertia. So that greatly simplifies the task of creating concentrated masses from our board components. Next, we'll ensure a congruent mesh for our shell mesh on our housing by stitching, as we did earlier with the bracket. Next, we'll create a shell mesh on the top of the housing. And we want to select just certain faces of certain bodies. And we don't want the board or the individual faces below each of the board components. So the element size of 0.1 is a little bit fine. Also, we didn't necessarily want a mesh for each face. So let's go ahead and undo that last command. We use the predictive toolbar to select creating a shell mesh again. We'll make sure we select polygon faces and deselect the board faces. We'll select an element size of 0.2. And we'll also make sure that we're not creating a mesh for each face. which I just toggled off. So now we have one mesh for all of those faces. We'll go ahead and first edit the mesh collector to assign a material of titanium for the top of the housing. And again, we'll inherit the thickness of the shell elements from the mid-surface. And another way that we can visualize the thickness is by plotting the thickness contours. All right, that looks good. Now, if we wanted to, we could create our own materials instead of taking them out of the library. And here you can see we have a number of different types of materials from which to choose. For an isotropic material, here we'll go into the material create dialog, and you can see all of the various characteristics of the material property that you can specify, starting with mass density and mechanical properties like Young's modulus and Poisson's ratio. We also have strength properties for ultimate and yield strengths, durability, thermal properties, coefficients of thermal expansion, conductivity, specific heat, latent heat, so that you can easily specify your material properties. Those properties can also be captured into user-defined libraries, which we'll use a little bit later in the demonstration. Continuing on meshing the housing, next we'll mesh the board. At the same element size, but into a new collector, because the board is not going to be made out of titanium. We'll specify a different material property for that. All right, so the board will be made out of epoxy. And the thickness will inherit from the mid-surface. Here I'll name the collector so that we know what the material is of the meshes that are in it. All right, we've inherited the mid-surface thickness. Next, we'll go ahead and mesh the bottom of the housing. And the bottom of the housing is going to be made out of a laminate. So I want a separate mesh for each face here. We'll begin by specifying the collector property as being a laminate. For that laminate, we'll inherit the properties from a layup, which we'll create in just a moment. We'll specify shear stress for bonding and our favorite ply failure theory. Now, to begin, we need to be a little bit more careful with the mesh properties, things like element normals. We need to make sure that the element normals are all consistent. So we'll go ahead and display them and make sure that they're all pointing outwards. That looks good. Next, we also want to ensure that we have a consistent material orientation direction. So here we'll check that next. And you can see that there is no consistency in the material orientation direction on our meshes. So to specify that, we'll first select some meshes that can have the same material direction. And we don't want that first one. I'll do a Shift mouse button 1 to deselect it. Then we'll edit the mesh associated data, select a vector method for specifying the material orientation, and then select an edge to define that vector. And then we can see that we now have a consistent direction for all of our material orientation vectors for those three faces. Now for the remaining two, we want a different direction. For the face on the right, we want the vector pointing downward. And for the face on the left, we want the vector pointing upward. All right, great. So now at this point we're ready to define our global layup. We could, if we owned FiberSim, which is a great tool for doing laminate design, import the plies from there in an HDF5 format. Or, since this one's pretty simple, we do have the ability to create global layups within Simcenter 3D, and that's what we'll do right now. So here we'll create a layup starting by creating 4 plies, and then we'll select ply material that we'd like to apply, and we'll use a unidirectional ply material. And the matrix and fiber materials I have specified in a custom library that we'll use. So here earlier I had created a matrix material. We'll specify a matrix volume fraction of 40%, and then a fiber material also from this same library. With a fiber volume fraction and a finished thickness. All right, so now we have our material specified. Here you can see the thickness has been brought in. Next we'll specify our fiber angles. For each of the plies. And now we'd like a repeating pattern of those 4 plies. So we'll copy it and then paste it above, but symmetrically first. And then we'll just paste it above again, which will be symmetric to the previous paste. All right, now we have our layup defined in terms of the plies. Next we need to define where we want the various plies to be laid up. So for the odd plies, we want to drape those on these 3 faces. We'll also select a start point for the draping, and we'll use the material orientation that we had specified earlier for the direction. Next, we'll drape the even plies, and we'll drape those on these 3 faces. And we'll use the same start point. Okay, so we'll go ahead and update our global layup and zones. Here you can see that 3 zones have been created. Let's take a look at the layup in different locations. Here we can see on our bottom face of the box, you can see all 12 plies. On the left side, you can see our odd plies, and on the front face, you can see the even ones. All right, so that's our composite definition. Here you can also see all of the plies. If you'd like, you can view fiber orientations here as well. So since ply 11 was only on those 3 faces, we're seeing the fiber orientation on those 3 faces. If we select a different ply, there's a different 3 faces. We can view the fiber orientations on those faces. All right, that looks good. Now we have one more thing to do, which is to connect the components that we had defined with concentrated masses above the board and connect those onto the board. I'll go ahead and chop off the top of the box with a section view so we can see inside a little bit better what's going on. And here I'll use the predictive toolbar to create my 1D connection. It's also available on the home ribbon. I'll do a 1D point-to-face connection with an RBE2. RBE2 is from the Nastrian solver language that we had selected for our environment. And we'll create 3 of these point-to-face connections, and we'll put them all in the same RBE2 collector. All right, because they're the same color, it's a little bit hard to see. One thing that we can do to make the visibility better on the model is to set our model display preference to color basis to the physical property table. So each mesh that resides in a different mesh collector will get a different color. So that way you can see all of the elements that have the same physical property table assigned to them. If we don't like any of the colors, we can manually adjust them as well. So for the 1D elements, we'll go ahead and change the color. Now let's just go ahead and do one of them first. Let's bring the color basis back to default so that we can make those changes, as opposed to having it assign whatever color it wants. So here we'll make our 1D RBE2 elements cyan. And they're a little bit easier to see now. All right, we'll go ahead and save that, and we have the finite element model definition for our entire assembly completed at this point. So we'll next create our assembly FEM, or our assembly finite element model. So we'll also be in the Nastrian structural solver environment. And here you can see it's inherited all of the components and their orientations from the engine assembly CAD model, which we can leverage to automatically map our finite element models that are associated to those CAD models into our assembly finite element model. So here you can see that multi-use bracket that we had meshed earlier comes in its 4 locations. So now that we have the model assembled, let's go ahead and connect the brackets to the engine case, which is ground. So I'll create a point between the 2 bracket holes there on either side as a center point for our ground location. And I'll connect it with rigid elements to the holes on the brackets. Next, because we've assembled a number of finite element models, there could be conflicts in the element and node numbers and plies and all sorts of different coordinate systems as well. Here we can specify an offset if we'd like to control exactly where those nodes and elements will be in terms of their numbering, or we can just simply automatically resolve any conflicts, which is what I've selected. We'll go ahead and save that, and next we'll create our simulation model. The simulation model is where we'll define our solutions, apply our loads and constraints. First, we'll create a linear static model, but here you can see in the Nastrian solver environment we have multiple different types of solutions, from nonlinear to modal. So here we'll create a linear static solution. We'll specify some specific output requests that we'd like in addition to just the default stress and displacement. We'll also go for grid point forces and glue results, which we'll use in when we're post-processing a little bit later. All right, now we'll connect the brackets to the electronic box with surface-to-surface glue. We'll manually specify a source region, which will be on the electronic box. And these faces are just a starting point for how it's going to create the glue. Then we'll also connect it to these faces, and it will only connect the faces or nodes that are within the search distance that we specify. And the distance from the bracket to the box is just a little under 0.7. Now, if we were to create some contact, you can see we have different types from standard to no separation. We won't be using any contact in this solution today, though. So we have a load case that we'll call our temperature load. We'll begin by creating a temperature set to put our temperature load into. Now we have all the units you can specify in whatever units you're comfortable. So we'll put a default temperature of 20°C for our temperature load. And then we'll assign a temperature load to all of the geometry in our model. And we'll import the temperature load from FlowEFD. So here we'll import it into a field, which will be temperature versus Cartesian. We'll use a Delaunay fast interpolator, and for any values outside of the table, we'll make them constant. Now, the temperature values from FlowEFD were in C, but the locations of those temperatures were in inches. So we'll have X, Y, Z in inches and the temperature in C. Now, there were some duplicate values from FlowEFD, so we'll tell it to use just the first occurrence of the X, Y, Z location. We could use average if we wanted to, if there were different temperatures at the same location. But just for simplicity, we'll go for the first. And here is a comma separated values FlowEFD temperature table, which we'll go ahead and import. So here you can see all of the rows from the FlowEFD model that it imported, XYZ temperature. We've got about a little over 24,000 lines of temperatures. And then we can go ahead and plot the contours of that temperature load. Since the FlowEFD mesh was different, unique from this structural mesh that I've just created, we can see how it interpolated those temperature values onto our model. Here we're looking at those temperatures in F, but similar to everywhere in NX, you can select whatever units you'd like to display those temperatures. So here we're looking at them in C now. All right, that looks good. Next we'll create another subcase, which will be our G-load. Now we could put the G-load in the same subcase if we always wanted to look at both, but if we want to look at either separately or scale one versus the other, it's very easy to do that if we put them into different subcases. And here I'll specify my gravity load in G's. We'll put in 10 G's in the -y direction. And that will be applied to all bodies in the simulation model. So I don't need to select any bodies in specifying my G load. Okay, now we'll put a fixed constraint at the center point for our rigid elements that are connected to our bracket. Now before we solve, let's take a look at some of the solver properties. Here we have an option to put in parallel solve, where we can do either shared memory or distributed memory parallel, specify the number of processors. I have a default which is set up for my computer. I have 6 cores, so I always want to use all of them in my solutions. So we'll go ahead and leverage that and solve. This particular model, we'll go ahead and not pause the movie while it's solving. Here it's writing out the deck. Now it's started up Simcenter Nastran, and we get a solver monitor that shows us the elapsed time for the solution. We also can see the convergence of the graph, and here you can see the elapsed time at the bottom has been 12 seconds. And let's go ahead and take a look at our results. All right, first we'll look at the displacements from our temperature load subcase. Here you can see the box is trying to grow. Maximum displacement's about 20 thousandths of an inch. Here for our G load, you can see the board inside is deflecting at about 1/10 of an inch, a little over. Here we can animate those results as well. We can also take a look at our stress results. And we're not seeing any results on the bottom of the housing because those are laminates. For that, we need to look at our ply stress results. Here we can look at XX, YY for ply 2, ply 3. We can look at XX, YY. Now, how do we know where our worst stress is? We'd have to go through all of the plies and take a look at all of the stresses. Or we can create an advanced laminate post report. Here we'll go ahead and select the linear static solution that we just ran, and both of our subcases, both of our load cases, and we'll use that for creating our laminate post report. So that will combine those two subcases to show us where the worst stress is across all of the plies. So here for our input, we'll take solver stresses and strains. For our output, we want at the absolute maximum across all plies for stress, failure index, and strength ratio. All right, so we'll go ahead and generate our results file for our laminate post report. And we'll begin by taking a look at our max absolute stress. Here you can see XX. If we're wondering where the max or the min is occurring, we can turn on our annotations. And when you're looking at XX and YY, it may not be the maximum that's the most important, but let's go ahead and turn on our critical ply ID. So this shows us what ply the max and min is occurring on, or actually the ply that has the maximum stress for that particular element. So here you can see our max is occurring at ply 3. And here we can see our XX stress and the ply that has the min here is, looks like ply 3. All right, so that's laminate post-reporting. And it looks like the min is also the absolute largest stress, also in the same location. And also on the same ply 3. All right, so if we wanted to combine those load cases outside of a laminate post report, we can combine those load cases right here as well. We'll create a combo load case where we put both temperature and G-load in, and we can put in whatever scale factors we want for each of those load cases. And then we can view those results. You can see how our max stress at 0.118 for our displacements for the combo is a little bit larger than the 0.116 for just the G-load alone. Not too much though. All right, next we'll create a result probe. To begin though, we need to create a result variable which will be used by our result probe. And we'll select the displacement magnitude result. We'll call it DISP, the vector magnitude for the displacement, which we'll use in the definition of our max disp probe that we'll create. So here we'll use that result variable and we'll select the entire model and find the maximum across the entire model. And we'll put that out to our listing window. So there's that 0.118 that we saw earlier that was in our combo combined load case. All right, so that allows us to see what that maximum displacement is without actually opening up our results. Let's go back to our stress results. And next what we'll do is create an XY plot of the stress across one of the bends in our bracket. So we'll create a query curve that will find the stress along the length of and go ahead and plot it. So there you can see stress as a function of path length. All right, next we'll create a free body to see what the loads are on our weld in our bracket, right along this weld line here. So here we'll do free body results. We need to have our grid point force results in order to be able to do this. I'll go ahead and select some elements that are up along that edge. Then I'll select my nodes on that edge. I'll go ahead and box select those. All right, and then select a location to sum the moments about. Here you can see the forces will be displayed in red and the moments in blue. And we'll go ahead and say OK. So in red here you can see our free body load is about 45 pounds and our moments are about 6 inch-pounds. All right, next let's take a look at some of our glue force results. And here you can see those element faces that have been connected with glue. And I'm going to select the glue magnitude result for all the faces on all of the brackets and dump that right into Excel directly. And what I'm really interested in is most of our reaction force through the glue is going to be due to our G load, but you can see our node as well as XYZ location and XYZ reaction force. You can see the reaction in X is pretty small as it is in Z, pretty close to 0, but Y, here you can see it's minus 91 pounds. That's going to be an important number. Let's remember that for some other things that we'll do next. So minus 91 pounds is due to that 10G load mostly on our electronic box. Now another way that we can create that result automatically is with a nodal force result, nodal force report, where we'll select that glue force type and select those same bracket faces. And we can specify a solution index from the load cases that we had defined, but we're really interested in that last one, the combo one. And we'll go ahead and add all the forces and moments and put that to a listing window. So here you can see that 91 again. That's the sum of all the forces for our glue reaction for the electronic box. Now just to confirm that, what we'll do next is we'll get a mass of the entire electronic box and see how that compares to the 10G reaction load. So here you can't see it, it's off the bottom. Solid properties check is what I'm going to select. And I'll box select all of the elements in my electronic box. We'll put the results in pounds, inches, seconds. So here you can see we have 0.02 pounds second squared per inch for our mass. Let's go ahead and convert that into pounds. So I'll copy it from that listing window, paste it into Excel, and multiply it by 386. Here you can see our 91 again. Let's get a few more decimal places there. And let's just turn it into a general number as well. All right, so there's our 91. Or 9.1, which is due to 1G, but due to 10 Gs would be 91. So that looks good. All right, next we'll do some response dynamic solutions. For response dynamics, we need to begin by creating a modal response dynamic solution. And because we're evaluating an electronic box mounted on a fan case of an engine that spins at 6,000 RPM, the frequency range of interest is going to be between 1 and 100 Hertz if we divide the 6,000 by 60 to get RPM into Hertz. But we'll go up to 200 Hertz because we'll go 2 times the frequency range of interest. So we'll drag our face, or actually add our face glue and temperature definition from our linear static run into our modal solution, so we don't have to specify that again. We'll just bring it right in. But for our constraints, we don't want a fixed constraint on that central node. What we want is first a user-defined constraint, which will constrain all degrees of freedom at that central node that attaches all of the brackets, where we'll define the direction of the excitation from the imbalance of the engine. So we'll fix everything except for the imbalance direction, which will be DOF2, which will be free. And then for that imbalance direction, we'll specify an enforced motion location and an enforced motion degree of freedom in DOF2 as well. So that's the direction of the imbalance that the rotation of the fan of the engine will impart on the box. So we'll go ahead and solve that. I paused the video. It takes 42 seconds to solve that modal solution. And we need that modal solution for our response dynamics solution process that we'll create next. We'll keep the rigid body tolerance at 1 Hz, so any modes below that will be excluded. And let's take a look at those 12 modes that our modal solution came up with between 1 and 200 Hz. There you can see all of them and where they occur. If we want, we can take a look at what those modes look like as well by post-processing those 12 modes. Here, I'll go ahead and step through here. You can see our first mode is a board mode, as are the next 11 modes, or actually 10 modes. Because our 12th mode, here you'll see, is actually a box mode, where we get the brackets and everything moving there. You can animate that as well. Luckily, that is 2x our fan red line, so we don't have to worry about that, but it's one of the modes that we've got now. All right, next we'll put in a viscous damping factor for all of the modes and evaluate the transmissibility of the circuit board. We want to take a look at the acceleration, and we'll put our input motion type as a displacement at that central enforced displacement node, which we had defined earlier. We want to take a look at the results, and just so we can see the board a little bit more clearly, let's turn off our loads and our simulation objects. And we'll select a node on the board. We want to look at the result in Y, and we'll put in a few extra spectral lines in our transmissibility XY plot. So here you can see the relative acceleration due to the various natural frequencies that occur between 0 and 100 Hz. So if we open up our results, and just so we can see 32 Hz is right about at that first peak, we can do a probing mode, or better, peak probing mode, so that way we'll jump right to the peaks in our graph, and you can see what the acceleration per displacement is for that at 32 Hz and at other various natural frequencies that we'd captured. All right, now we have a curve which defines the energy that the imbalance of the engine imparts. and that's our low rotor imbalance curve that we'd like to add to our available curves that we can use for defining events for our frequency response analysis that we'll do next. So I'll create an event. Here you can see we have numerous types of events, from random to response spectrum. For this particular event, we want a frequency response analysis to see how much the board is going to react to the engine imbalance. So for that, I'll define my excitation, again at that central node. And we'll use that rotor imbalance that we just brought in as our excitation. Now we could create a new one if we wanted. It's great to be able to reuse curves though. You can see what type of function it is. It's a spectrum. We can do a quick plot of it to see how the energy increases quadratically with the frequency or the speed of the engine. The acceleration increases there with frequency. All right. So now we've defined our excitation and our frequency response analysis. Now we can evaluate the function response to get an XY plot of the acceleration at a point on the board and at our original excitation location. We'll look at those results in the Y direction, and we'll go ahead and plot it. So this shows us the sympathetic addition of the response of the board at that first mode and how it actually is a little bit less than the excitation in some other locations. But this would be an area of concern. We'd want to make sure that the engine doesn't dwell at any of those particular frequencies. Luckily, that's below our idle speed of the engine. Idle speed of the engine is at 50 hertz. But as it goes through, when it's starting up, you can see it's getting hit with 8 Gs on the board at that particular location. Now, if we're wondering what the peak acceleration is across the entire board, because we just picked one location, we can create a contour plot of our peak acceleration. We'll give it a name. And we'll select all of the nodes on our board with the Smart Selector feature angle nodes. Now we also want to include in that selection our components, the concentrated masses that represent our components, so we can see what the acceleration is on those components as well in the Y direction. All right, and that takes just a few seconds to generate a contour plot, which we can view. Now let's go ahead and turn off the elements. And here you can see in inches per second squared what the acceleration is. Let's go ahead and put that in Gs, so we have a requirement to keep our accelerations on our components and our board below 10 Gs, and you can see that they're all well within 10 Gs, although we do have one area here that's somewhat above it, but luckily it's not a component that would be shaking. If that was of a concern, we could stiffen the board in that location locally. Next, we'll look at peak stresses on the board. We'll go for the VM stress, and we'll select feature angle elements to get all the elements on the board. And we don't need to select the concentrated masses because those will not have any stress results in them. So I'll do a shift pick to deselect those. All right, and then we'll look at our contour results for our stresses. Again, turning off the element edges, we'll go for an average stress as well. And you can see what our stresses are on the board due to our peak response. All right, that looks good. Next, what we'll do is make a CAD change. The first CAD change that we'll make will be to the electronic box on the board. There's a hole. And this particular change is going to come from the analyst, Andy. He doesn't have right access to the master CAD geometry, but he does have the idealized part, so he can make some changes to that to see what kind of an effect that change would have. And I'll show you how Ed, the engineer, can incorporate that change into his model. So to do that, we'll use master model dimensions. It's the only way that we can do that to bring those changes back into the master CAD model. So this hole that we're going to be modifying is currently 2 inches in diameter. We'll make it smaller to 1 inch, and you'll see right away that our mid-surface model has updated, and it's telling us that the master CAD models are read-only and that you can't save those changes to them, and that's fine. We'll tell Ed about it, and Ed can go ahead and save it. So right now, as Andy, we'll go ahead and save all of our simulation models and the idealized part and those master model changes that we made. Now, one other thing that we can also capture, because we're running managed, is we can decide which simulation result files we'd like to bring into the database as well. We may not need all of them or even any of them, but we can easily pick and choose which ones we want and say import selected files. All right, and here's another good warning saying that our master CAD files are read-only and you can't save those. All right, so next we'll go and log in to Teamcenter as our engineer, Ed, who has right access to the master CAD geometry. And Ed will fire up NX. And let's make NX a little bit smaller here. All right, that looks good. And Ed will go ahead and open up the I part for the FADEC that Andy just changed. So he'll search for that FADEC asterisk to get the I part. Go ahead and open that up. Here he gets a good warning from Teamcenter saying you don't own this part. It's already open and checked out by Andy. And anything you change to the I part can't be saved. So that's a good message. Here it's telling us that it's right locking the master part because of some inner part changes that were made. And those are the changes that Andy has made that he wants us to incorporate into the master. So here we'll go to our master part and we'll go ahead and take the top off the box again so that we can see a little bit better with the section view. And you can see that that hole has already been made smaller. And as Ed, maybe he doesn't know exactly what changes Andy wanted to make just by the description that he told us. So what Ed can do is look at all of the expressions in the model, and he'll see the ones that have an inner part change that have been made to them with that padlock. And if he's wondering where is that expression used, you can do list references, and it will tell us that that particular that expression is used in feature 29, diameter 1 hole. So now Ed can go find feature 29 diameter 1 hole in the part navigator and see where that hole is. All right, so Ed likes the change. He's going to go ahead and incorporate it into his model. So to do that, he's going to remove the right lock on his FADEC, and he's going to close the eye part to remove that inner part expression from the part as well. But the change remains. Then he can go ahead and save his FADEC. Just to double check that that change has remained, you can see that the hole is still at the smaller diameter that Andy had specified. All right, so while we're still Ed here and we have right access to all of the master CAD geometry, we're going to make a change to one of the brackets, or to all of the brackets actually, since they're multi-use. We're going to make a change to one of the gussets. We need to reduce some weight from the engine. And when we were post-processing first time around, we noticed that the stresses in the gussets were pretty low. So we'll go ahead and put a lightning hole in it. And we'll put in a hole diameter. And okay. All right, so now Ed's done with his job. He's going to go ahead and save his bracket. He's going to call Andy and say, hey, I made some changes. I incorporated the change for the FADEC. And I've also made another change which I'd like you to incorporate to the bracket. So first thing Andy's going to do is close and reopen that bracket that Ed just changed. Here we can see we get a message saying the part was different on the disk and it was successfully opened. So let's go ahead and take a look at that bracket as Andy. You can see what the change is. All right, it's added a hole. Let's go to our idealized part, which is where we created our mid-surface representation of the bracket. And you can see that that hole has been incorporated into the mid-surface. Next, we'll go to our finite element model. And we get a message saying that the geometry has been updated. All of the stitches that we made to make a congruent mesh also have updated. Now all we need to do is update the mesh, and we can see that the hole now is incorporated in our finite element model. We've still maintained all of our material properties, physical properties, and stitch elements to make a congruent mesh. All right, next we'll go to our FADEC. And here you can see the geometry has been updated in our finite element model of our FADEC as well. The geometry is updated, but the finite element model has not updated yet. We'll go ahead and hit the Update Finite Element Model button. And now our finite element model has updated. All of our connections of our concentrated masses to that circuit board have been retained. We'll go ahead and update our composite global layup and zones. Now we'll go to our assembly FEM, and we'll go ahead and update our assembly label manager to resolve any conflicts with the mesh numbering. Next we'll go to our simulation model, and you can see all of our solutions and constraints, loads, glue, everything has been maintained and survived the CAD update because it was all assigned to geometry. So to keep our linear static solution results, I'm going to clone that linear static solution and we'll call it linear static 2, and I'll go ahead and solve it. And this will run so that we can see the effect of those CAD changes. Here, I'll pause the video. Again, 13 seconds to solve. And we'll look at our results side by side. So here we'll load our linear static results. We'll look at a top and bottom. On the top, we'll put our original G-load displacement, and on the bottom, we'll put our CAD Change updated G-load displacements. And then we'll go ahead and synchronize the views so that anytime we rotate one of the views, the other view will follow, and we'll be looking at the same thing. All right, so maybe it might be a little bit better to take a look at stress results here, because that's why we put the lightning hole in. We'll go ahead and take a look at our element stress results, and we'll take a look at the before and after around the lightning hole for stresses. We'll look at average stress, and maybe we'll do banded view as well. All right, so that looks good. Still the stresses are low around the holes. Probably had a very small effect on the performance of the assembly. But we can also go ahead and replay those probes. Here you can see our max displacement. On our updated solution. And we can also take a look at our nodal force report, again, for our glue results. And that concludes the demonstration.